Okay, hello everyone. So this is going to be part two of the first or second workshop, I suppose, the first workshop that we're doing online. As promised, this is going to be about isomerism. So it's a bit of a recap from year one, but these are still some useful things that you need to sort of remember. We might ask you to apply these things not just this year, but also next year, when we're trying to sort of bring together some of those key concepts in chemistry. Okay. So this is going to go through all the main different types of isomerism, some examples, and then you can hopefully apply it to a few questions so you can see some of the differences that we have between them and when we might use one over another. Again, if you've done part one of the workshop, you can see actually isomerism is quite important in carbohydrates, and we use some of this terminology for carbohydrates, which we'll see in a minute, but this will allow me to go through each of them. This should be a little bit shorter, this video, so it should be fairly snappy in terms of going through each of those key isomeric differences, I suppose. Okay, so if we follow it through, again you can follow through with me on screen. Again, hopefully you would have done these answers on your own, but if you haven't, you can work through with it with me today. And again, we're revising knowledge about stereochemical descriptors. When we're dealing about isomers, there's different ways of describing different isomers. Now, if we go to the first question, the first one that we're going to deal with, and hopefully these aren't completely new to you, but the first stereoisomer type we're going to deal with is E and Z isomerism. Okay, so if we come to question A here, we're going to try and use the E and Z descriptors to denote which of these two structures is E and which one is Z. Now these are isomers of each other, so again you can look at them and think about they've all got the same functional groups, they're just attached in slightly different configurations. I'll try and pick out the key points of each of the isomers and why they're different, because sometimes it can get a little bit confusing about when you would use one over another. Now importantly, if we're looking at EZ, an important factor is that we have an alkene in reality. So hopefully you can remember what an alkene is. But an alkene is obviously we have a double bonded carbon to carbon in the structure. And this is what allows us to have isomers. Because basically when we have a double bond here, these groups, if I can just circle them very quickly, these groups now can't freely rotate, okay? They're held in position, as are these. So the whole molecule itself can rotate, but this side and this side themselves cannot rotate, and they're fixed in this configuration. Let me just get rid of those. If I can do that a bit speedier, that would be useful. Alright. So if we have a look at the structure and what it's called, obviously the name doesn't change between the two. They're actually the same molecule in terms of their chemical composition, but obviously the isomerics are different. You can see that they're not arranged in exactly the same format. Again, we have this hydrogen proton here in this structure next to our chlorine, and in this structure it's next to our bromine. Now there are a few sort of easy steps, and again once you've learned the steps they're not difficult today, so again it's just a bit of a recap. First thing to do if you're looking at EZ isomers is best to draw a kind of an imaginary dotted line straight through the middle of your structure. So now we're splitting it into two halves here, so we've got half one over here, we've got half two over here. Now if you remember about EZ isomers, we have to denote the priority of the groups over one another. So the first step that you always have to take is assigning priority either side of this double bond, so in section 1 and in section 2. So this functional group with these two functional groups individually. Okay. So if you're denoting priority, higher priority is the atom with the highest atomic number. Okay. So if you don't know, you might have to work out what the atomic numbers are that are important. If you don't know that, you're going to struggle to work out priority. But we only ever use very common ones: carbons, chlorines, bromines, protons, oxygen. There's nothing else we're going to particularly throw at you, or we would give it to you in the question if there was something particularly odd. So you need to know the atomic numbers of the key ones that are bound directly to our carbon here. Hydrogen's a nice easy one, so hydrogen is just 1. Okay, so hopefully you remember these a little bit in terms of what some of the others are. So carbon's 6, okay, chlorine is 17, and bromine is 35. So again, you might need to look these up if you've forgotten them. They'll be in the periodic table, so you can go back and have a look at using your periodic tables. But that's the atomic numbers of each of those molecules, or atoms, sorry, within the molecule. So as you can see, we've got 1 and 6, and we've got, 17 and 35 on this side. So what we need to work out is either side of the double bond, whether the top or the bottom has the highest priority. And again, whichever has the highest atomic number is basically given priority over the other atom. So if we compare bromine versus chlorine, bromine has the higher atomic number, we'll give that a 1, and chlorine has the lower atomic number of those two, which is 2. Okay, we're not comparing them across the double bond, we're just each side of the double bond when they're on the same, like here. Hydrogen is 1, carbon is 6, so carbon has the highest atomic number. Now if they're equal, we need to go to the next atoms attached, but in this case we don't have to worry too much about that. So we denote carbon as being number 1, and we denote hydrogen as being number 2. Now if I get rid of some of the other numbers, which might just confuse matters a little bit at the moment, so I'm just going to get rid of the sides. I'll get rid of the atomic numbers as well. And I'll get rid of these. Almost there. Okay. Okay. So when we have that, we can look at basically which side of the double bond the 1s and the 2s are. So if we look at the top, so now we're comparing these two against each other, and we're comparing these two against each other. So in this molecule we had a number 1 and a number 2, and in this molecule we had number 2 and number 1 at the bottom. So we've got a 1 and a 2 and a 2 and a 1. So if these numbers were the same, it would be a Z isomer. If they're different, as they are here, that means this is the E isomer, or E isomeric form. So we'd denote this as E, and that E would go at the front of the name. If we quickly buzz through how that compares to what we have in our other isomer, hopefully you also see that this one is different. So if we do the same and assign priority, bromine's number 1, chlorine's number 2, versus hydrogen, which is number 2, versus carbon, which is number 1. So if we look at this time, we have both number 1s at the top, and we have both number 2s at the bottom. Therefore, the number 1s are on the same side of the double bond, and therefore that is denoted as the Z isomer. Okay, and that's all you need for denoting E and Z. Working out priority, again, you must have this double bond. Without a double bond, we don't have this isomeric possibilities necessarily. We'll come to some options later where you still can with chiral centers, but when you have an alkene like this, we can assign based on how the groups are associated across the double bond. Okay, so that's a fairly nice one to start with. We'll come back to priority in a later example, so we'll cover that again a little bit more. This one was just quite straightforward, I suppose, and most people would have come across what we call cis and trans isomerism. Now, again, you might think, well, we've got a double bond here. Are we not just doing E and Z again? Well, there is a time when we use cis and trans instead, or can use cis and trans instead of E and Z, and it's when we have two functional groups that are the same across either side of the double bond. So in this structure here, they're not shown automatically, but we have hydrogens that are not drawn in. Okay, so as you can see, either side of the double bond in this molecule, okay, we have a hydrogen, opposite side we have a hydrogen. On this one, again, it's an isomeric form, where we just have the hydrogens almost flipped one either side. So if we compare that back to what we had here, all four of the functional groups are different. Okay, when we have them, when we have ones that are the same, we can actually use a slightly simpler way of denoting isomerism. So what we're doing here is we're comparing whether these two are on the same side of the double bond, or whether these functional groups are the same or whether they're different. So this molecule here, you can see that they're both the same, they're both at the bottom, okay? And if they are the same, that is the cis isomer. If they are across, they're different, okay? So this is on the opposite side from the other proton, that is what we call trans. Say trans for being different, okay? And that's how you would denote those two. Again, the trans and the cis go in front of the name, and they'll be able to tell you, again, without drawing the structures here, if I said it was cis for methylpentane 2-ene, you would know the configuration of that particular molecule. So always draw in as hydrogens and then look on what side of the double bond they are. Okay. So we'll move on to one that you don't see very often, which is the D and L notation. Okay, so we've got D isomers and we've got L isomers. Now these are only used for carbohydrates and amino acids. Okay, so this takes us back to our kind of Fisher projections that we talk about, or we went over a little bit in the first part of the workshop. It's a bit of a historical numbering system or lettering system, but it's still useful and it still stands up, and it's just a way of denoting the differences between two carbohydrates or two amino acids, which structurally are very, very similar. Again, this one is quite straightforward, and again we'll only look at it when we have it in a Fisher projection. So you remember our Fisher projections are kind of our open ringed system, and the one that we're looking for is we're looking at the hydroxyl group on our bottom chiral carbon. Okay, so we're looking at the hydroxyl group that's bound to this carbon here. So we're looking at these hydroxyl groups here. Okay, so not the one at the bottom, not this one, not that one, not that one. It's basically the bottom chiral carbon that we have. Now this is actually quite easy to work out your isomers from here, because what we're looking at is the way that the hydroxyl group is pointing. So it's either pointing in this direction, like it is here, or it's pointing in this direction, horizontally, in our other isomer. Okay? Now, fortunately this is fairly straightforward, but if it's pointing to the left, that is the L isomer, and it's pointing to the right, it's the D isomer. And again, the L and D go in front of the name of the carbohydrate or amino acid. So that's a nice straightforward one. You've got your Fisher projection, you can easily use that L and D terminology to say which isomer is which. Okay, that's a nice straightforward one. Again, you don't use that very often, but it's worthwhile not to confuse. You know, you might not be sure which one to use, but you would know that L and D is only useful for these carbohydrates or amino acids. Okay, so we've only got one more to go, so this is fairly short and snappy today to go through these. And this is RNS, which again is used quite a bit. Now as you can see, what have we got different from what we've seen before? Okay, so we've got a chiral carbon. Okay, it's not bound to anything as in having an alkene or anything like that. So no, we're not going to use our E and Z from earlier, and we're not going to use our cis and trans because we don't have that double bond. Okay, it's not a carbohydrate or an amino acid, so we're not going to use the L and D. So we have a final one, which is RNS. This can be used to denote isomerism in structures where we have these chiral carbons. Okay, remember, a chiral carbon is a carbon where it's bound to 4 different functional groups, okay, or 4 different atomic groups that we have around here. So if you look at this one, we've got a methyl group, we've got a carboxylic acid, we've got a proton, and we've got an amine there. They're all functionally different, so therefore we've got 4 different groups acting on that carbon or bound to that carbon. The important thing here is to denote the arrows that we have here. So this means that this is pointing basically from back towards you, so it's behind the screen, and then we have this one here, which would be me looking at the carbon itself from in front of the screen. So just remember that they are orientated in real space, and that's what those two arrows are there to denote, and they're quite handy for doing that. If my eraser would like to work, we can get rid of those. Now the important thing to remember about when you're doing RNS, now there is a trick if this is not the case, but for RNS, always make sure that your proton, okay, is at the back, okay, so it's pointing towards you from behind the screen or behind the piece of paper. There is a trick that if it's not, that you can actually reverse the type of isomerism, but for the moment we need to make sure that this proton is pointing from behind the screen or behind the piece of paper toward you. Okay, that's important because it's obviously the orientation of all of the other atoms in this structure will change depending on where this proton is and where it's rotated. So if we push it to the back, it's got the lowest priority, as it always will have, being a hydrogen, so we're always pushing a high priority to the back. Now from here it actually follows fairly similar rules to our E and Z isomers that we had at the start, where we need to look at the groups that are directly attached to our sort of central chiral carbon in this case, rather than double bond. So what do we have? We have a carbon, we have a nitrogen, we're forgetting this proton, okay, so it's out of the way, and then we have another carbon here. Alright, so it all comes down to priority again. So if we just put in the atomic numbers of the ones that are directly bound, so we've got 6 for carbon, 6 for carbon, 7 for nitrogen, I believe. I'll just double check. I do have a habit of forgetting them from time to time. Yep, number 7. Okay, so obviously now we have two groups that have got the same priorities, and we've got the nitrogen here, which has got the highest priority. So now we've worked out which has the highest priority, we can give that a 1. So I will just replace our 7. I'll get rid of our 2 6s as well for the moment. So our amine group is our highest priority group. Now we said these two carbons are obviously going to have the same priority as carbons, they've got the same atomic number. So what we need to go is we need to go to the next atom bound to that carbon. Okay, so for this one here, we've got 3 hydrogens bound to it. Obviously they all have an atomic number of 1. If we have a look at this, we've got a double bonded oxygen and we've got an OH. Okay, those bond angles are horrible, but it represents what's found in that case. Now oxygen has an atomic number of 8. Okay, so therefore we'd compare the 8 versus the 1 that we have here. Okay, so that would mean that our next highest priority group is our carboxylic acid at the top. My eraser tool is a bit slow at times. Okay, so we can denote that as being number 2, and then we'll denote this carbon here as being number 3. Now from here it's actually quite straightforward, we just need to look at the order of the numbers, whether they go clockwise or anti-clockwise around the central carbon. So if we look at where it goes 1 to 2 to 3, and then back around to 1. So this is anti-clockwise. And anti-clockwise is the S isomer. Okay, so that's what we would denote here. Again, the S would go in front of the molecular name. Quite often it's put in brackets, but just to denote the different isomerisms. So if you see a bracketed R or bracketed S before your molecule, you know that it's the anti-clockwise arrangement around that chiral carbon. Now, I've compared this to the other isomer that we have. So we've worked out what the priority of the groups are. So we know that nitrogen is number 1, we know that this one is number 2, and we know that this one is number 3. Again, if we follow it round, so you can see actually this time round, they are in reverse. So this rhymes, they're going clockwise around that carbon, and clockwise is an R. Okay, so you do need to remember a few of the key points in terms of which way round these are, but a lot of people remember at least to how they would assign priority. Now the only thing that I said at the very start is that obviously we normally push the lowest priority group, normally a hydrogen. I can get rid of all my arrows very quickly. I'll leave that there for the moment. So for instance, if we switch these two arrows around, and this one became the block arrow, and this one became the dash, you'd still assign the priority in the same way that we just have. Okay, so this would still be number 1, this is still number 2, and this would still be number 3. Do the order, it still looks clockwise. But if the proton is in front of the page pointing in, we need to reverse, or we just swap over the type of isomer that it is. So if they were the other way around, it would not be an R, as it initially worked out. You need to reverse it, and it would become the S isomer. Okay, so that's only when the proton, lowest priority group, is not at the back. Okay, so away from the page pointing towards you. That's the only time when you need to do that switch. Okay, you can also rotate the molecule around in real space or in your brains to work out and put the hydrogen at the back, but normally it's much easier to just do this swap to work out which isomer it is. Okay, so that actually brings us to the end of that second part of the workshop. Again, it's a bit of a recap for isomers from part 1, but this stuff is useful for you to keep in your brains and keep sort of testing yourself to make sure that this doesn't disappear and you don't lose this sort of knowledge, because it is important, it's fundamental knowledge, which you will find useful throughout the rest of the course. Okay, so again, that is it from this part of the workshop. We'll be following up with workshop number 3, again via the video formats, and then again you can follow it through once you've had a go at the worksheets yourself. Okay, that is it from me, and that is bye. Enjoy working your way through those problems, and then move on to workshop number 3 and see how you go with those slightly different problems. Okay, that's bye for now then.